Molecular Orbital Theory, or MO theory for short, you might hear it called. This is really just an extension of the last lesson on valence bond theory, and we'll just take it just a little bit further and find out it's a little bit better reflection of reality. Now, this is the fourth lesson in the first chapter of my brand new organic chemistry playlist. I'll be releasing lessons weekly throughout the 2020-2021 school year, so if you don't want to miss one of these, subscribe to my channel, click the bell notifications. You'll be notified every time I release one of these. Okay, molecular orbital theory. Now, we talked about valence bond theory, and we talked about how, like in a molecule of hydrogen, H2, we have s orbitals overlapping. And we said that, oh yeah, those orbitals overlap, and electrons live in these overlapping orbitals, and life is good. Well, it turns out the picture's just a little more complicated than that. And it turns out when orbitals overlap here, two things happen simultaneously, and it gets a little complex from here. Now, it turns out orbitals, again, are three-dimensional depictions of what we call wave functions. And these wave functions are just big three-dimensional math equations, if you will. Now, you've seen like your sine function again, and your sine function can have both positive and negative values. And from 0 to pi, it takes on positive values. From pi to 2 pi, it takes on negative values. And right at pi, you have a value of 0, which we call a node. Now, your sine function, this is just a two-dimensional wave function, whereas again, our s orbitals, our p orbitals, our hybrid orbitals, all those things are actually three-dimensional wave equations. But in the same sense, they can take on positive values as well as negative values. Now, in a p orbital, you have a node right at the nucleus. And on one side of that node, the wave function's positive, and one side it's negative, and it could be either way, positive on top, negative on bottom, or positive on bottom, negative on top. Either way. But your 1s orbital that you have for hydrogen, there are no nodes. And so, but the wave function can either be all positive or all negative. And as a result, you've got two different types of overlap that might occur. Now, in this case, let's just say it's all positive on both sides. Well, if it's all positive on both sides, then the overlap is going to be what we call constructive overlap, and it's going to lead to an amplification of the wave functions in those regions where there's overlap occurring and things of this sort. However, if one side's positive and one side's negative, so then the wave functions are actually going to lead to what we call destructive overlap, and they'll start actually canceling each other out. So if we take a look at a couple of sine functions here, we can kind of get a better picture of this. Let's say we got a sine function here, and then we've got a sine function here, and I'm going to have them move towards each other. So instead of having a couple of s orbitals moving towards each other, as we would with two hydrogen atoms approaching each other, we're going to have a couple sine functions approaching each other. And so we've got areas where we have positive versus negative, negative versus positive, and we're going to have them overlap till this rightmost region on this one overlaps with this leftmost region. And as we see, when they overlap, but this region where they overlap, they're both negative. And when you add negative values together, they get more negative. And that's what happens when you have constructive overlap, is the parts that overlap have the same sign, either both positive or both negative. And that part of the wave actually gets bigger. But you could have exactly the opposite happening here instead. So let's switch this guy here. And once again, we'll have these wave functions move towards each other till they overlap just a little bit. And that's going to change the result here. And so now we got positive on the far left. We got negative on the far right. And then right in this region where they overlap, they're going to cancel perfectly. And there's no wave anymore right there. We've created a node, as it turns out. And so we call that destructive overlap. So if the parts of the wave functions that overlap have the same sign, both positive, both negative, constructive overlap results. If the parts of the wave function that are overlapping have opposite signs, one positive, one negative, then when you add them together, they cancel, and we call that destructive overlap. Now, the same thing occurs with, again, these s orbitals in hydrogen. Your s orbital is either all positive or all negative. And it turns out you can't really say it's one or the other. It's more of an and situation. And so when these two s orbitals come to overlap, both possibilities occur. Both what we call in phase or constructive overlap occurs, and then out of phase destructive overlap occurs, and they happen at the same time. You can't just say, well, Chad, you told me the s orbital is either all positive or all negative. Yeah, but it's also kind of both possibilities at the same time. And so when the overlap occurs, both constructive and destructive overlap occur simultaneously. It is a really, really weird thing. So, but let's see what kind of happens here. So if we get constructive overlap, so again, if they're both positive or both negative, I'll make them both positive, but all of a sudden then this area where they're overlapping actually gets amplified, and you end up getting a big, giant orbital. So, and this big giant orbital engulfs both nuclei. So notice we have these two individual atomic orbitals, each with their own nucleus. Now we have this big giant orbital engulfing two nuclei. Because it's not for a single atom, it's now for a molecule. That's why they call it a molecular orbital. Now, simultaneously, it turns out, we could also have these two orbitals having opposite signs. So, and where they overlap, they'll actually cancel each other out. And so I like to draw the same picture I drew for constructive overlap for destructive overlap. Draw something looking very similar, and then get my eraser out, and then erase right down where they overlapped. Cool, so right where they overlap, they actually cancel this time around. And so you get something looking like this. This is one orbital. It's got two little regions here, but we just created a brand new node. And so when you're doing both constructive and destructive overlap, no creation of a node, but destructive overlap is always going to create a node right down the middle between the two nuclei. Cool. We call this lower energy one a bonding molecular orbital. So, and it's lower energy for a couple of main reasons here. So if you look, where's the best place for an electron to hang out? When an electron's negative, the nuclei in the atom are positive, and so the actual best possible place, if we kind of like highlight where those nuclei are, the best place for an electron to exist would be right in the middle. Well, that's the part where the overlap occurred when it was constructive overlap, and that's the part where the wave function gets amplified, and that therefore becomes the most likely place you're going to find an electron. And so now the best place for an electron to hang out is the most likely place for an electron to hang out, and that means it's going to be lower energy. When things are where they want to be, so to speak, based on their forces, that lowers their energy. And so we get a bonding molecular orbital here that's lower in energy. Also, because we amplified this region, actually we get an increase in the volume of where the electron can exist. And according to the Heisenberg uncertainty principle, that also lowers its energy, but that's not the most important thing in the world. So it's much easier to see that, yep, electron gets to be where it wants to be, lowers the energy. Now, on the other hand, with this, what we call the antibonding molecular orbital, so in this case, the absolute best place for an electron to exist, we just created a node there. There is zero electron density right there. The electron can never be there. And as a result, this actually would be a higher energy orbital for an electron to exist. Okay, so let's take a look at the typical MO diagram we draw for this kind of a setup. So usually we fill the typical boxes like you'd see for the 1s orbitals in hydrogen, and they each have an electron here. So there's your original 1s orbitals, and we kind of look at this as a vertical scale of increasing energy. And so this would be kind of like non-bonding energy of these two separate s orbitals, so before they've overlapped. So they're just completely separate. But once they come together and overlap, it leads to a lower energy orbital and a higher energy orbital that get created. So I'm going to draw those in a different color, although we usually put them in the same color on a diagram, but I want to put them in a different color so we can kind of keep them distinct. So here's these original atomic orbitals, and they're atomic because they're still separate atoms, but once they come together, those atomic orbitals don't exist anymore, and now what exist are these molecular orbitals, the orbitals of an entire molecule that envelop more than one nucleus. Cool, and so now we have an option. Now that these exist and these don't, we got to figure out, well, where do we put these two electrons? As separate atoms, they just were where they were in these 1s orbitals, but now we have a choice. We can put electrons down here, or we can put electrons up here. Well, we'd much rather put them in a low energy position, and we have room for two electrons down here, so that's where we put them. Cool, now we call this turns out this is a sigma bond, end-to-end overlap here, so we call this the sigma 1s molecular orbital, and we call this one the sigma 1s antibonding molecular orbital. And so it turns out that if you look at in black here, we've got represented the original atoms, and in blue here, we've now got represented molecular hydrogen. And we can see that the electrons before bonding, as compared to the electrons after bonding, they're lower energy overall after bonding has taken place. And this is why bonding taken place. So bonding is only going to take place if the electrons end up lower in energy, and in hydrogen's case, they definitely do. Now let's take a look at one more thing in this regard and come all the way over here. So we often draw you a lovely diagram for bonding. So in this case, we often show something effect of this guy right here. We'll put energy here, and we'll put, I'll call it bond length, but it's really just the distance between the two hydrogen nuclei. So when you get all the way out here, you just have two separate hydrogen atoms. So that's at kind of the 0 energy point here, and that's kind of like this right here. So, but as these hydrogen atoms come closer and closer and closer together, so we often label this R here, so you get them closer and closer together, you reach a minimum in energy, and we call that point right there, that distance, the bond length, or the mean bond length, or something along those lines. And we see that it's lower in energy than two separate atoms, exactly for the picture the reason we see in this picture of molecular orbital theory. So the electrons are lower energy when they're in this molecular orbital than when they're in these two separate 1s atomic orbitals. And so that's kind of depicted on this diagram. So as you go from here to breaking them apart, it costs energy, or when you form the bond, it's going to release energy because it ends up lower energy. So that's kind of the idea. Sweet. So this is molecular hydrogen. We often define simply what's called the bond order. So for these MO diagrams as well. And bond order is kind of analogous to like single bonds, double bonds, triple bonds. A bond order of 1 would correspond to a single bond. A bond order of 2 would correspond to a double bond. A bond order of 3 would correspond to a triple bond. But you can also have like fractional bond orders as well. Like a bond order of 0.5 would be like half of a bond. A bond order of 1.5, 1.5 bonds. And we don't really have like an analogous Lewis, designation for that. Now with resonance, we can kind of talk about such things, but we'll see we have a direct way of looking at that when it comes to MO theory. Now let's say again, we look at that picture of H2. So formula for your bond order is you take the number of bonding electrons and you subtract the number of antibonding electrons. They call them antibonding because they tend to pull the nuclei apart and do the exact opposite of what a bond did. A bond holds the nuclei together, an antibond pulls them apart. And so antibonding electrons actually can kind of cancel out bonding electrons. And so to calculate bond order, you take the number of bonding electrons, you subtract off the number of antibonding electrons, that would be canceling some of them out, and then you divide by 2 because it takes every 2 electrons to make a bond, just like we learned with Lewis structures. And so here we've got 2, and again, we don't look at the atomic picture, just the molecular picture right at the center. We've got 2 bonding electrons. We don't have any antibonding electrons. So in this case, you'd be 2 minus 0, all divided by 2 gives you a bond order of 1. And so for H2, we'd see that we've got this bond order of 1. Now, a couple things we can do. Let's say we take H2 minus. So if it's got a negative charge, it means we've added 1 extra electron. And so in this case, well, the bonding molecular orbital is full. So if we're going to add an extra electron, it's going to have to come up here into the antibonding molecular orbital. And so now we have 2 bonding electrons minus 1 antibonding electron, all divided by 2. And 2 minus 1 is 1, and divided by 2 is going to get us a bond order now of 1/2. Cool. Now it turns out H2 minus still exists. To exist, you've got to have a bond order greater than 0. Well, that is greater than 0. Probably not the most stable thing in the world, but it is greater than 0. And so this species is likely to exist. Now, if we go the other way as well, take that electron back off, we'll start with just plain old H2, and we look at H2 with a plus charge. And to get a plus charge, now we have to remove an electron. And so in this case, I'm just going to take one of these out. And if we go to calculate bond order now, so in this case, you got 1 bonding electron minus 0 antibonding, all divided by 2, and you also get a bond order of 1/2. And again, another species that is likely to exist. It may not be the most stable thing in the world, as that's a rather weak bond, but it is possible that it exists. And the reason I bring that up is because now we might compare this to something like helium. Now, helium, on the other hand, has 2 valence electrons in its 1s orbital. And so those 1s orbitals come, they overlap, it creates a lower energy sigma 1s bonding molecular orbital and a higher energy sigma 1s antibonding molecular orbital simultaneously. But now we've got to fit 4 electrons into this molecule. And so there's 1, 2, but then there's 3, 4. And now we have a problem. We filled up not only the bonding, but we also filled up the antibonding. And when we go to calculate bond order here, and I should have made this diatomic helium, so which doesn't exist, FYI, and we'll see why in a second. You take 2 bonding minus the 2 antibonding, which is 0, and then divide by 2, and you still get a bond order of 0. And that doesn't exist. And in this case, diatomic helium doesn't exist. Helium is not diatomic, it's monatomic. And now we can explain why it doesn't exist. Because it would have a bond order of 0, and a bond order of 0 corresponds to no bonds at all, i.e. it doesn't exist. Cool. Now a couple other things we should talk about. So let's turn this back into diatomic hydrogen one more time. Okay, so specifically we're going to apply this to H2. So in this case, there's not really much to talk about because we only have 2 molecular orbitals, but on bigger diagrams where you have more molecular orbitals than just 2, so these get a little more complicated, and we'll deal with those in a chapter on conjugated systems much further down the road in this course. So, but in this case, it turns out there's special molecular orbitals. And again, the molecular orbitals are the ones in blue right up the center here, not these atomic orbitals that we started with in black, but the molecular orbital is the one we want to focus on. And the highest energy one that has any electrons gets a special name, and that is the highest occupied molecular orbital, or sometimes people say the highest energy occupied molecular orbital. So, and call it the HOMO for short, and it's just the highest energy orbital with electrons. Now, same diff, your lowest energy molecular orbital that has no electron in it, that's empty, we call it the lowest unoccupied molecular orbital, or the LUMO for short, also gets a special name. Now, we might have in other more complicated and more complex diagrams, we might have more lower energy orbitals that are all full and more high energy ones that are all empty, but your HOMO and your LUMO get special names. They're part of what we call the frontier molecular orbitals. And the reason they get special names is that those are usually the ones involved in chemical reactions. If you're going to need to donate electrons, you'll donate your highest energy ones in the HOMO. If you're going to need to receive some electrons, you want to put them in the most stable, lowest energy spot you can into the LUMO. And so we'll find out that these are the ones often involved in chemical reactions, why they get special designations. So, and you might have to identify in some molecular orbital diagram, either the HOMO or the LUMO or both. Okay, so now we want to take a look at the same principle, but with pi overlap, which always again involves sideways overlap of p orbitals. So, and again, take a step further than what we saw in valence bond theory and apply the fact that, again, both constructive and destructive overlap are going to be occurring simultaneously. And again, if constructive overlap occurs, it's going to lead to a lower energy bonding molecular orbital. If destructive overlap occurs, it's going to lead to a higher energy anti-bonding molecular orbital instead. Okay, so as we said again with our p orbitals, you got a node at the nucleus, and again, one part is positive, one's negative, and it could be either way. So, and when they overlap, you have to consider that constructive overlap could possibly happen, and that means in this case the wave functions match where the overlap occurs. So, and when that happens, it leads to a lower energy bonding molecular orbital, and so in this case, you see that this region right here, it's going to get bigger, and this region right here, it's also going to get bigger. And again, you have the nuclei. Actually, I drew them in black here, so I should probably draw those in black. You'll have the 2 nuclei still right there. Cool, and now the top would be all positive and the bottom all negative. Cool, and that's your bonding molecular orbital. And again, the best place for an electron to be would be as close to the nuclei as possible in this orbital, and that would be along this center line. Notice they can't be here because there's a node there with p orbitals no matter what. So, but that is the part where constructive overlap occurred. The most likely place for electrons to be is the best place, and this is your lower energy bonding molecular orbital. Now, the other possibility here, yet again, is that destructive overlap occurs. And again, constructive and destructive always occur simultaneously. You always create both a bonding and an antibonding molecular orbital at the same time. It's just a really weird thing with molecular orbital theory, but it is a great and more accurate depiction of reality. This really does happen. So, but in this case, when you get destructive overlap, it always leads to a higher energy orbital. So And it always leads to the creation of a node right where these overlap. And again, just like we did with the s orbitals overlapping, I'm going to draw my constructive overlap picture. And then I'm going to pull out my eraser. And right where the destructive overlap occurs, that's where I'll erase. That's where they cancel each other out. And so that is one big molecular orbital. It's got 4 different areas of electron density, but it is one molecular orbital. And again, plus, minus, minus, plus. And so we already had a node right here to begin with. That was there from the get-go. But now we've created a new vertical node as well. And again, destructive overlap always leads to the creation of a node in your antibonding molecular orbital. Constructive overlap will not create any new nodes. We had one node to begin with. We still only have one node in our bonding molecular orbital. In this case, we would call this the pi 2p bonding molecular orbital. We call this one the pi 2p antibonding. We always use that asterisk to signify the antibonding. And same kind of thing we saw with the diagram for molecular hydrogen. So here now we're going to have the 2p orbitals, one each with an unpaired electron. And they come to overlap. It's still going to form a lower energy bonding molecular orbital and a higher energy antibonding molecular orbital. And now only the pi 2p, the bonding, is going to have electrons. And so yet again, we find that this molecule is going to be more stable than separate atoms, and that's why we create a bond to begin with, because it overall lowers the energy of the electrons. Cool, so you might have to recognize an MO diagram like this. You might have to identify the HOMO and the LUMO, things of this sort. You might have to calculate bond order, which again in this case would be 2 minus 0 over 2, which would be 1, and that would be just the pi bond. But notice this would be an incomplete diagram, because in addition to pi bonding, before you can have a pi bond, you already got to have a sigma bond as well. So this is only looking at the pi part of things. So, but much more commonly in an organic chemistry class is you're going to have to identify some of these molecular orbitals. And so a pi 2p, you'd have to recognize this kind of a picture. Pi 2p antibonding, you'd have to recognize this kind of a picture as well. All these sorts of things are things you're on the hook for. And again, this idea that constructive overlap and creation of a bonding molecular orbital and destructive overlap and creation of an antibonding molecular orbital occur simultaneously. And again, it doesn't matter that one might be empty and one might be full, but both exist and both are created simultaneously. It's just kind of a weird occurrence that is the way nature actually exists. Cool, if you've benefited from this lesson, give me a like, give me a share. And if you're looking for practice materials and the study guides that go with this, check out my premium course on chadsprep.com.